Welcome everybody. Welcome to the Sustainable Chemistry Lecture Series. My name is Antonietti. I come from the MPE in Potsdam. And I will tell you today a little about scale and some thermodynamics of the climate change. It's a strange title, but I promise it to be less boring than the title sounds. And the whole thing, of course, will be done from a chemical perspective. So what is climate change and how we define climate change? I think the most important curve indeed is this very famous CO2 curve. It's measured on the tip of a mountain in Hawaii, far from everything. And as you see from this curve, the data are recorded for a long time. And here you see a track record for the last 50 years. And this curve essentially is exponentially increasing. And you hear the reflection of that 1,000 times. Some of you will now find out it's not exactly exponentially increasing. There's a little ondulation on top. And you see how precise this measurement is, because in winter, of course, less CO2 is consumed where plants grow in summer. And this is seen as a yearly change within the CO2 curve. And then, of course, the beginning of my story, we have a number of climate conventions. We are aware of sustainability. And in 2019, we started the biggest experiments on Earth on climate unintentionally. Corona came and we stopped essentially all international air traffic. It was a dream for all the people who don't like airplanes. No airplanes were leaving. The air in China and in Europe was clean again because big power stations had to shut down. Cars were not driving. Most of us spent that time in their home office. So the question is, what did this do to the climate curve? And here, of course, scientists are lucky because they can access the raw data. And in the raw data curve, you see, in fact, the increase of the CO2 was bigger than ever. So in spite of all the obvious factors were moved out, indeed, we were spoiling our planet even more. And the answer is rather simple. And it's somewhere else than many people expected, but it is well known. It's the internet and our data use. So as you see with these transparencies, meanwhile, the internet is the biggest sink of energy. At least more than 30% of the electricity are going onto the internet. And if you go through the numbers, data centers on this planet is taken away about 200 terawatt hours per year. And you are allowed to add, indeed, transmission networks to the distribution, 250 terawatt hours, and taking YouTube alone, is 11 terawatt hours. So when all of us were hiding in the cellar, of course, we had the wish for communication, and we were using the tool which avoids isolation the most, which means the internet, and we more than overcompensated everything we did just by data use. There's a scientific aspect of that and, of course, a social aspect. Every generation has its own disease. Our grandparents loved to ride cruise sailboats. I have an expensive car, explosion engines, which I hardly have time to ride. And the young girls of nowadays take TikTok and YouTube. And by streaming, indeed, we do a bigger harm than we do, indeed, by using classical fossil tools to generate a climate change. You can express it in a local scale. So streaming, and it depends where you take the numbers from. I take a very positive number for streaming, is about 400 grams of CO2 per hour. So if you decide for a nice movie in the evening, or indeed stream some of your hits, it's 400 grams of CO2 per hour. And if you think now about 7 billion downloads, or indeed massive parallel multiplayer games, you are easily in orders of magnitude which are beyond your expectation. So obviously, there's little to do because we cannot disallow people to move, and we cannot disallow them to use the internet. And the solution, of course, then is very simple. If you're not a scientist, you put one of these wonderful boards on that, and you see the end is near, And I took this from a very friendly person in the Mauer Park of Berlin, and what you see for a can of beer, I'm now in the hand of the future of this planet. But this is only one answer, and I would not be here and try to give a lecture if this would be the complete truth. Yeah? So in the very end, and this is a personal statement I have to say, 25 years ago, this was already visible, and I decided in the very end to do something for the future, but by doing chemistry. So the Fridays are for chemistry, and chemistry is for future. Yeah? Politicians cannot change anything because they manage something. They can give frame conditions, and from the many disciplines in science, only a few are made to change something. And you can open the Encyclopedia Britannica, and there it's written, chemistry, the science that deals with the properties, composition and structure of substances, the transformations they undergo, and the energy that is released or absorbed during these processes. This is chemistry, and be aware, CO2 is a chemical molecule. And if you want to bind it, collect it, transform it, be very sure this will be a chemist or maybe a microbiologist. So indeed, we can do something, and this should be not only my answer, but all of your answer. Yeah? It's a science problem, and personally, and you will see in the whole lecture series, if we're able to reinvent every process, every step in science, then we have a real chance to come up with a sustainable society. And of course, the beginning of all these changes is to make a balance. In this lecture series, you will hear about biorefinery, about polymers, about degradation, about eco-recycling. But we have to start in the very end with a balance that you see what are the numbers, how to do it, and what is the scale of the problem. And this is the agenda of my lecture. Yeah, we first analyze the scale of the problem. What is the size of the climate problem? Then we will talk a little about biological processes. And then I may introduce at the end a hybrid terraforming technology, where terraforming only means to bring back the planet as it was. So this is the balance. On the planet, we have 4 gigatons of oil every year. This is the public production statistics. A gigaton, giga sounds great, yeah, is a cubic kilometer if density is 1. So our oil drilling is 1 kilometer times 1 kilometer times 4 kilometer. This is a lot. And it comes with a lot of money. You know that certain countries earn trillions, in American notation, of dollars, yeah. And it comes, of course, with the climate change, because from this fossil oil, about 50 gigatons of CO2 are created. And if you sum up over all human activities, this includes cement manufacturing, coal, and other sources. These are about 30 gigatons of CO2. And this is exactly the increase you see in the CO2 curve on this mountain on Hawaii. We do regenerative energy, but you have to note that the relative contribution of all these windmills and solars is 20% at best. Yeah? Because in the very end, the problem is much broader than only electricity. Yeah? And what we have to do now is please invent a technology for this size, 30 cubic kilometers of CO2, yeah? And best to a price which is not more expensive than the oil which it's made of. So the cost should be about 10% of the oil, then people will accept it. This is social reality. Can we easily collect the CO2 of the atmosphere? And here, of course, the physical chemist tells you no. Yeah? The problem is not first law of thermodynamics, it's like second law of thermodynamics. Because in spite of having too much CO2 in the atmosphere, CO2 is still very dilute. So 420 ppm are parts per million. And if you want to collect it, you have to turn it from 420 parts per million to 1 million per million. Yeah? And this, of course, we are happy. We can calculate the amount of entropic work which is needed. This is, of course, is essentially given by our good old Gibbs relations. And what you see with this simple calculation, indeed, that the energy it takes to avoid dilution is terrible. It's 10 to the 18th joule. Yeah? So it's much too much. We can construct a machine and we come up with prices. An ideal machine, Laplace machine, which can control everything in detail, it would take €6 to collect a ton of CO2 from the atmosphere, just providing this entropic work. Yeah? And if you take real machines man can build and man can pay, it's around 120 to €200 per ton of CO2. So from this side, collecting CO2 from the atmosphere to make a further process is too complicated, too large, not payable. Yeah? And again, still many people do it, but be clear that entropy works against you. And if I learned something in my 30 years of teaching, never work against entropy. This simply does not work. Yeah? The good thing is we have to open up our mind, and in this case even a chemist looks at biology, because there are beings which do exactly this process. And these are plants, of course. So the poor plants, they are, as a tree, practically poor carbon. So a tree is made in solid matter, 40% of carbon, and is eating air. So from these 420 ppm, a tree can condense. It provides very important entropic work. And according to thermodynamics, if we calculate this entropic work, a tree has to spend as much for collecting the CO2, providing the entropy, as it can do to build up biomass. So a tree has a heating value, and a tree has a CO2 collection value, and the CO2 collection value, depending how you count, is at least as much as the heating value. And this we usually don't appraise. So if you have biomass available, take the biomass because this is collected CO2. Avoid the machine to collect the CO2, but take the leftovers of trees or plants because this is still full of the entropy work, and this entropy work you can build a technology on. So the trick of solving the collection problem is a super simple trick. Let other work for you. And in 30 years of experience, I learned that this always works. To let other work for you. This is good. So we have now the biomass. What to do with the biomass? And we know biomass is a labor good. We can eat it, microbia can eat it. If you leave biomass in the oven, either in your fridge, or indeed in open nature, it will vanish again. It's metabolized and turned into CO2. So our chemical task is, let's take this biomass, apply a simple process which must be cheap, and turn it into a version of biomass which is not degradable anymore. And of course, it's a little bit more complicated because biomass also contains nitrogen and phosphor, and this you should not shut away. So just packing big plastic bags of biomass will not work because then we deplete the planet on nitrogen and phosphor. So we have in the process separate phosphor and nitrogen. And this, of course, on please the 7 gigaton scale. What type of product we need on such a scale? Because now you have 70 gigatons of carbon, you have found the magic process to turn plants into the product, but then we have a mountain of 7 gigatons of this carbon product. Is there anything in human society which is big enough for 7 gigatons? And here, chemistry is not. The biggest product on Earth, polyethylene, polypropylene, goes with about 200, 250 million tons. This is a factor of 30 smaller. There are two other products who could match this scale, and one is building industry, concrete, and the other is agriculture. And agriculture, of course, is the point I want to address to, because there's an eager need of carbon in agriculture. So a special type of polymer you will see we need indeed in agriculture, and this is another problem which we did not talk about, which is as big as the climate change. This is the big picture, what you see over here. So if you now really make scales, you will see that the 415 ppm CO2 in the atmosphere have an overall mass of carbon of 870 gigatons. So integrating the whole carbon in the atmosphere is 870 gigatons. We take now all plants, we calculate all plants, all land biomass is much less. So all land biomass is around 550 gigatons. This is also why the idea planting trees will not really work. Because you can plant trees, but you cannot put so much biomass on top of the already existing biomass that it will really match the other number. The third number you see in this diagram is the real one. This is the amount of carbon in soil. And we know soil is black, sometimes soil is black, this is carbon. Yeah? And if you just integrate over the so-called top layer, top soil layer on this planet, you come up with a very different number, which is 1500 gigatons. So you see the only scale really matching with the atmospheric CO2 amount in carbon is soil. Only a little addition of fertile black matter to soil will cure the atmosphere. And this is meaningful because we have a big problem with soil. Yeah? There are some side calculations I should tell you before. Is there hope? Is there future? And I already told you biomass grows with enormous rates on this planet. So the rate it grows is around 60 gigatons per year. This is carbon equivalents. And if you relate these 60 gigatons growth of biomass per year to the atmosphere content, you see that this is worth 28.6 ppm of atmospheric CO2. This is hope, because it means plants eat every year around 30 ppm. We add every year 2 ppm, but plants eat 30 ppm. And of course, we could calculate the principal best recovery rate, and you see within 3 to 5 years, our atmosphere could be back to pre-industrial standards if we would control the process completely. This is too much, as you know. It's enough if we compensate 3 to 5 ppm, so we know that we have to treat about 10 gigatons of agricultural waste, side products, turn it into fertile soil, and then the climate problem is solved. So you see, we have now a number of things accomplished. We have, in principle, an analysis. We know what is worth doing, how it's worth doing. Of course, now only the chemistry is missing. How can we turn biomass into artificial soil? And this is a chemistry problem. It's essentially even a colloid chemistry or polymer chemistry problem, because the materials are well known and the conversion schemes from biomass to humic matter, to artificial humic matter, are well known. People will be very happy, I should say. So in this diagram, and this is from the World Agricultural Organization, you see the speed, how fast mankind is destroying their fertile soils. Overfarming, misuse, greed essentially makes people to extract more and more of harvest from soils. And if you look at the map, Europe is in a good shape, but China, Africa, Central America, Brazil, the big plains in the US, all of them losing fertility and carbon content with a speed which is scary. So no, if you go on like that, we will not die of overheating in summer. We will die of hunger. And the good thing, of course, is that global problems are always related to each other, which means maybe we can recover the soils by doing this terraforming technology, which means keeping the standards of carbon in soils higher by a technique, by a chemical technique. This is not invented by me. You should know that at the famous Paris Convention, the Paris Climate Protocol, indeed there was a big group of about 1,000 people, and they called themselves the 4 per 1,000 initiative. And they calculated the same things and said, if we are able only in the fertile soils of these planets to increase carbon content by 4 per million, 4 per 1,000, fertility is safe and climate is safe. So this is the lever we need, this is the balance we can use without stopping watching internet, using explosive engines, or maybe have a flight once a day. This is the point. So we have essentially a technical solution, which now, of course, turns into a scientific problem. The real fun thing is now you can go to anthropology, and what you see over here, this is the so-called terra preta, black earth, in the Amazonas. It's an indiogenic technology. It was invented 600 years ago. Then indeed the Spanish came with the measles. These people died, but the locations of these settlements in the Amazonas is still there. And you see here a nice picture. Yeah, essentially, when you go to these spots of artificial earth, you see that corn or maize is growing very well, whereas of course in jungle soil is a ferrous soil, maize does not grow at all, because essentially all the nutrients are washed away. So using carbon for improving artificially fertility of farmland was invented up to 7 times. It depends how you count and what you count as an invention, but we do already practically for the lifetime. This was done those days in clay reactors, so people indeed built enormous figures, they put it below earth, for safety of course, and then they essentially converted the biomass of their farmland, food leftovers, everything they found into those reactors to fertile soil. This is of course what we now envision for the complete society. Me, of course, as an educated Middle European, my cultural heroes are in the north of Scotland, and it's essentially the country where whiskey is coming from, and this whiskey country also knows artificial salts. So usually Scotland, and in this case these are the little islands north of Scotland, this is flat as a wind-polished stone. But if you go to these islands, you can see spots of super high fertility, which is artificial land created in the very end 6,000 years ago by Celtic people. And they had nothing except 2 things. They had a lot of algae, kelp, because they were at the ocean, it's an island, and this is why it's only on islands. They took this kelp, mixed it with calcium carbonate, seashells, and observed that within a few years it turned into black salt. So even the recipe is clear. Take biomass, take algae, take a base. Calcium carbonate is just a special type of base. Take ashes and you can handle the reaction. The reaction is a base catalyzed conversion of otherwise degrading biomass to, in this case, remanent black soil, because as I told you, these special soils, they're called macher, are over 6,000 years old. It's sustainable. So, not today, but because I promised only statistics today, we will learn in this lecture series on hydrothermal humidification. It's essentially a base splitting of carbohydrates, and now you can apply all the modern techniques like NMR, IR spectroscopy, and that, and you can follow indeed how biomass slowly turns under influence of a base towards humic matter. The prices, as you will see, are low, so in the very end even the price dimension is okay as long as we have enough waste biomass, and believe me, we have enough waste biomass. This not only points into the past, because you have to say, we in Germany love little houses and we love Berlin with its 6 floors, but there are parts on this planet which maybe count even more for the eco-balance of the planet, where people have to live in high houses. And what you see here is the future of Asian living. So one, of course, the upper right is a clear science fiction. It's so-called urban farming, vertical farming, where you build glass houses over each other to provide fresh food in the proximity where you live. It's calculated and it will work. You see a green city, the upper left one exists already. The lower central picture is the future, is Singapore 2. It's opposite of Singapore on the Malayan coastline. And they really built this city at the moment to be a green city. And the only thing I like to say, this is big market for chemistry, because all these buildings need, of course, good soil on their outside, first for climate preservation within, of course, but secondly to grow the plants on site, because we know plants need a substrate. So this is past, but this is also future. And let me sum up today's lecture. What I wanted to teach you is there is hope in the very end. Yes, CO2 is big in the atmosphere, but CO2 is only a molecule, chemists know molecules, and we can handle molecules. Not alone, but maybe 1 million people together, we can make it, because if you then divide the numbers, you will see that it's possible. It's hope because we have learned that the natural consumption rate of CO2 from the atmosphere, land only, not including oceans, is 30 ppm per year. So this is such a lever, such a strong power of biology, that biology will help us to cure the planet, as long as we help biology to do that. And this, of course, is exactly what we propose to do. Let's think about the chemistry of fertile soils, and let's help fertile soils to grow plants, to grow microbia, to bind the CO2. This is our lever. Yeah? I did not talk about the technologies. This will come later. You know, at the beginning the numbers, later the details. But be aware that the main problem always when you clean up a world is dilution, entropy. And the problem, indeed, CO2 is diluted, and this is why I feel very safe in my prediction that it will be not big machines built by persons, enormous air washers as we see them in science fiction movies, that we will do it in the hybrid bio way, because this is the only thing which is payable and which looks or feels natural to us. And we cannot talk about sustainable chemistry and then dream of machines of the size of 100 cubic kilometers. Yeah, this is, I would say, rather unexpected. This is bubble. Yeah. You will see, of course, that we will have many processes, and I think it's the many little things that will sum up to the whole pictures. Yeah. And of course, this is also not by me. This is the concept of a future industry. Currently, crude oil chemical industry is only covering a third of the possible economy. There are two further branches in that. One is indeed this type of conversion. So in the very end, to turn the biomass you find into something else. And the other one, of course, is to turn such products back to consumer goods. And like that, of course, you can close the sustainable cycle. And if I would show this diagram to a master of business administration, he would understand that it's not about restricting economy, it's about growing economy, but into the right direction. Thank you very much.